Hello, welcome to Recitation 11. The topics this week are basically the stuff that the first and second derivatives tell us about the graph of a function. I'm going to have a giant slide here to remind you of all of this, and specifically the second derivative test, which we didn't have time to cover in much detail first. So first, I'm going to start with the reminders. So we have here the definition of what it means for a function to be increasing or decreasing. But we should all know what this means when you're drawing the graph of a function. Here's increasing, here's decreasing. A function can also be neither, by the way. It could be a constant function, at least in some parts of it. Now, there is a relationship between the locations where the function increases and decreases versus the first derivative. And it's the second box here. If you're talking about a function that is differentiable on a certain interval, if the derivative is always positive there, then the function must be increasing. And if it is always negative, the function must be decreasing. So when a problem asks you to find the intervals of increase or decrease, this is usually what you have to do here. Just find the derivative, find the locations where it's positive or negative. But be careful, it doesn't work the other way. It's possible for a function to have like some points where the derivative is 0 and some other points where it is positive, and it's still increasing. So just because it is increasing does not mean that you're always going to have the positive derivative. You could have 0 derivative at some points. And the typical example of that is the x cubed function, which is always increasing, but as it approaches x equals 0, the derivative does become 0 for just one instant there. So just be aware of these examples. And then finally, first derivative test. The derivative tests, they concern critical points. They concern classifying them as minimum or maximum. So for this one, you just need a continuous function, which is differentiable around the point. So you're going to have some critical point A. The function does not need to be differentiable at this A. It only has to be continuous there, but it might also be differentiable. Those are the hypotheses. If you have that, you're allowed to use the test. And what does the test say? Basically, if the derivative changes sign around this point, then according to how it changes sign, you can classify it as local max or min. So more precisely, if you have a derivative that's positive before the point and negative after the point, then this point must be a local max because the graph is going to look like this. Or maybe the point is critical because the function is not differentiable there. There's a cusp. But what's important is that the graph was increasing first and decreasing later. So this is a local max. And you have the vice versa situation down here. If it's decreasing first, increasing later, this point must be a local min. And if the derivative actually does not change sign, then it cannot be a local extreme. So maybe the derivative was increasing first and continued to be increasing after that. This is a critical point right here because the derivative is 0. And you can see it's not actually local min or max. So this was all about the first derivative. Now let's talk about the second derivative. So now we have this notion of concavity. A function on a certain interval is going to be called concave up when the shape of the graph is a smile over that entire interval, and concave down when it's a frown. Again, well, over the entire interval. I guess I should not be drawing them like this with straight lines. If you have a straight line, that's neither a smile or a frown. So it's up to the author to define them as both concave up and down or neither. So rather, I should be drawing them more like this. I wanted to have examples where you have a cusp, you have a point of where the function is not differentiable, but the graph remains a smile or a frown. So these are examples. And what is called an inflection point, it's a point where the concavity changes, either from up to down or vice versa. So for example, like this, here's a graph that is concave up, and then suddenly it starts being concave down. this point right here is inflection. What happens at inflection points is that usually the second derivative is equal to 0, but that usually does not mean anything. It might not be. So what is the relationship between concavity and second derivative? Similar to the relationship between increase and decrease and the first derivative. If the second derivative is positive on an interval, the function must be concave up. If the second derivative is negative, concave down. And well, then if you have a point where the second derivative is changing sign, it must be an inflection point, because it must mean the concavity was changing. But be careful. Lots of things to be careful about here. First of all, it's possible to have a second derivative equal to 0 only at some points and then positive at other points, while f is still concave up. This is analogous to the previous remark about the x cubed function and the first derivative. So just be careful with this. Concave up does not automatically mean second derivative always positive. It might be the case that in a few points, the second derivative is 0. Second remark, it's possible that a point has a second derivative equal to 0, even though it's not an inflection point. The example would be the x to the fourth function. That looks like a parabola, but it's like more flat than the usual parabola. 0, if you compute the second derivative there, it is equal to 0. However, the second derivative is positive both on the left side and on the right side of that point. As we can see from the graph, it is a smile on either side, so this is not an inflection point. And finally, it's possible to have inflection points also where the second derivative does not exist instead of being 0, although it's kind of hard to write down examples. I think it was the x to the 1/3 function. Yeah, so you just be aware of this. And here is finally the second derivative test. We'll do one example of this right after this review. So once again, the derivative tests, they are about classifying critical points as local min or max. This one uses the second derivative. What are the hypotheses? Before you can use it, you need to have a function whose second derivative is continuous around this critical point that you have, and you have a critical point where the first derivative is already 0. This is important. It has to be like that. Then, okay, so now you have this critical point. You're trying to determine if it's local max or min. Look at the second derivative. If it's positive at that point, it must be a local min. Be careful with this. It is positive and minimum. You might think positive means maximum, right? But it's the other way. Very easy to think about why. Once again, just draw the pictures. If you have a smile, which means second derivative is positive around this point, it is local minimum, as you can see from the graph, because the point is a valley. If the second derivative is negative, the point must be a local max, because now you have a peak situation with a frown. But if the second derivative is 0, the test is just inconclusive. It doesn't tell you if this is a local max or min. Could be anything. So here is now the promised example that I wanted to do in lecture. What does the second derivative test say about the critical points of this particular function? So what you have to do is take the derivatives. We can do that very quickly here. 12x cubed minus 12x squared minus 12x plus 12. And that's it for the first derivative. And we're going to need the second derivative. 36x squared minus 24x minus 12. Okay, so the second derivative test is something that applies to the critical points. We need to find the critical points. So we need to take this derivative, which exists at all points, and set it equal to 0. Just as a reminder, critical points means the derivative either is 0 or does not exist. Does not exist is not something that applies to this case. This derivative always exists, but it could be 0. We have to solve this. You can see that you can factor a 12. There's a 12 everywhere in this function. Am I getting the signs right? Yes. So now this is a cubic polynomial. Usually you don't know how to factor that. It could be complicated, but this one is very easy. If you factor x squared from the first two terms, and then minus 1 from the other two terms. So this minus x plus 1 becomes plus x minus 1. You see that you have this x minus 1 in both terms now, which can be factored. And this is the complete factorization of this polynomial. So things like this involving very easy coefficients, usually they can be factored. You should try. I mean, we have to because we need to find the roots of this polynomial, the zeros. And we can see from here, x equals 1 because of the first factor is a possibility. And in the second factor, you have x equals plus or minus 1. So the critical points are 1 and minus 1. Two locations where the derivative can be 0. Now go back to the question. They're just asking us to apply the second derivative test. What does the test say? So the test, it says that you need to apply the second derivative to the critical points. If you find a positive number, it's local minimum. If you find negative number, local maximum. If you find 0, then it doesn't mean anything. That's all the test says. So now we need to take this second derivative function and apply it to the 2 points that we found. F double prime of 1 and minus 1. F double prime of 1 is 36 minus 36, 0. F double prime of minus 1 would be 36 plus 24 minus 12. So don't actually need to know the exact value, but it's clear it's going to be some positive number. So from here, only at minus 1, the test is going to be conclusive. Minus 1, because we found a positive value, must be a local minimum point. Local minimum point of f. But the test is inconclusive at the number 1. What does that actually mean? Does it mean 1 is neither? No, it's inconclusive. We don't know yet from the test. We can try other things if we want to determine if what 1 actually is. Local min, local max, neither. I'm not going to do it for this problem because it's not asking us to do it, and there will be another problem soon asking us to do that. But the answer to this problem is right here. So important remark, the second derivative test only applies to points where the first derivative is 0, always. Only those types of critical points. Yeah, so for example, consider any point different from 0 for the function f of x equals x squared, just as a quick example. F double prime is equal to 2. Like, consider the number 1, a equals 1. If you forget about this important detail here, you might want to say, look, f double prime of 1 is equal to 2 because it's always 2. That's a positive number. So 1 must be local minimum point. Well, no, that's not how the test works. Just because you found a positive second derivative, be careful. Doesn't mean that yet. This only applies to the locations where the first derivative is 0. Notice that this first derivative of 1 is not 0. It is also 2 because of this. So in this problem, you would only be able to apply the second derivative test to the number 0. That's the only location where f prime is 0. And then that's correct. It's giving you that this point is a local minimum as it is. So please don't apply the second derivative test to points which are not critical points. Okay, now here is the other example that I had mentioned. It's very similar, another polynomial. Item A is saying compute the derivative and verify that it coincides with this expression here. Essentially, they are trying to tell us what the factorization is going to be. Because if you compute f prime 4x cubed minus 15x squared plus 18x plus minus 7. You know that you're going to need to find the zeros of this later. That's going to be pretty much impossible if you don't know how to factor this polynomial. So they were nice in the problem. They told you, by the way, here is a possible factorization. Just verify that it works. So all we have to do is take this one that they gave us, expand it out to verify that this is really the same thing. And then that expression is going to be the one that we can use for f prime. So what I'm doing is multiplying this out. You can check the calculations. 7x squared, 14x minus 7. So after expanding out the expression they gave us, and now I'm going to group together the terms with similar degrees, you have a minus 8x squared minus 7x squared. That is minus 15x squared. 4x plus 14x, 18x. And then minus 7. So it checks out with the derivative that we found. So A was just very simple. Now we know that the first derivative factors this way. And now B is asking you, what do both of the first and second derivative tests say about the critical points? They want us to find the critical points and apply both of the tests. So B, let's find those critical points. Now that we know the derivative in factored form, that's easy to solve. Critical points are locations where this is equal to 0. So either x equals 1 for the first term, or setting the second term equals to 0 will give you 7 over 4. There are only 2 critical points. Okay, we're gonna also need the second derivative because we need to apply the second derivative test. So take f double prime. You can look either in the factored form of f prime to take the derivative. That would require a product rule, probably not very easy. Or you just look at the polynomial expression, take the derivative of that. That's much simpler. So you have 12x squared minus 30x plus 18. Keep this one, we're gonna need that. So now let's apply the derivative tests. Second derivative test. You need to take each one of the critical points, 1 and 7 over 4, and apply the second derivative to them. What do you get at the number 1? 12 minus 30 plus 18. I'm looking up here. Well, that's a 0. So inconclusive test. This test, unfortunately, doesn't tell you anything about the number 1. And f double prime of 7 over 4. That's going to be some annoying calculation, but we can do that. 12 times 7 over 4 squared minus 30 times 7 over 4 plus 18. So what is that? As it turns out, it becomes 36 over 16, positive number. So if you find a positive number, the point must be a local minimum. The point was 7 over 4. It's a local minimum. That was the second derivative test. Now the problem also asked us to apply the first derivative test. Let me just remind you how that works. First derivative test for critical points involves looking at the first derivative before and after the point. If it is changing sign, depending on how it changes sign, the point is going to be minimum or maximum. And if it does not change sign, then the point is neither. Okay, so we already know what the critical points are going to be. They were, once again, 1 and 7 over 4. So imagine that they're going to divide the domain into 3 pieces. 7 over 4 is larger than 1, by the way. You're going to need to know the sign of f prime in each one of the pieces in order to understand if it is changing or not. So what do? You're going to select points in each one of the pieces, like the point 0, maybe the point, like the pieces that involve infinity. You can also, you should try to select points which are very large, like 1 million here. We're going to see why for the third piece. And then in the second piece, unfortunately, we don't have many options here. Probably the point 1.1, something like that. That belongs to the second piece. So yeah, it's going to have to be a fractional number. Okay, so compute each one of those by using the f prime formula, which, by the way, I'm going to copy down here. Maybe I'm going to copy down the factored form, this one, x minus 1 squared for x minus 7. There's a little shortcut that we can try to do here to understand the sign of this expression. Namely, notice that the first expression is always positive or 0, like x minus 1 squared. That's not going to affect the sign. So you don't actually need to know the value of that expression. You just need to understand the second expression for x minus 7. That one's going to change sign at the number 7/4. So if you think about it that way, it's easy to understand what's happening. But if not, you can just plug in the numbers here. For example, f prime of 0, this part will be a 1, this part will be a minus 7. And then what about this 1 million? Why did I choose 1 million? Well, essentially, this polynomial, if you expand it out, it's a cubic where the first coefficient is positive. It's 4x cubed. That's the one that's going to dominate if you take a very large number, like a million. So 4 times the cube of a million, that's a positive number. So we don't need to know what this value is, but it's some positive number. And then what about 1.1? Well, that one, just do it with a calculator. So when you plug in 1.1 in the second factor here, that's a minus 2.6. And the first factor is just some positive number. So this is negative. All right, so we have the signs of f prime, negative, negative, positive. As I said, 7/4 really is the only location where it's going to change sign because of this piece. The first piece is not changing sign. Okay, so now based on this, you can try to sketch more or less what the graph looks like. Maybe like this and like this. Around these points, notice decreasing, 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 increasing. So from here, you can tell 1 is not an extreme point, but 7/4 is a local minimum point. That's the first derivative test. This conclusion we already knew from the second, but the second was inconclusive for the first one. Now it is conclusive. Usually the first derivative test will be more conclusive than the second, but the second is easier to apply. Moving on. A little bit of a different problem here. Given the graphs of f prime and f double prime, sketch the, by the way, the word continuous should be here, sketch a continuous graph of f, also in a way such that f of 0 is equal to 0. By the way, something like that has to be given because you know that if you only have the derivative or the derivatives of a function and you want to find the function itself, there could be many possibilities. Any function that you find, if you scale it, if you translate it up or down, that would also be a possibility. So by fixing a specific value, then you are determining the function. But let's look at item A, and I'm going to put the answer here. Okay, so we're going to try to sketch f. F of 0 has to be 0, so it needs to go through this point. Just have to understand what's happening to both f prime and f double prime. There's important numbers here, -5 and -2. So you're just going to look at the signs of each one of those. Before the number -5, f prime is positive. So I'm looking at here. That means the function is increasing. the f is increasing, but f double prime is negative. So it is concave down. A function that is increasing and concave down looks like this. So I'm going to be sketching like the pieces up here so we can see what the graph looks like. Now between -5 and -2, both of the f prime and f double prime are negative. So now it is concave down, but also decreasing, like this. After -2, f double prime became positive, so now it is a smile, but f prime is still negative, so it's still decreasing. So what is a smile that is decreasing? It's like this. Finally, after the number 0, both of the functions became positive, smile increasing like this. So you can see from here the general shape of the graph has to be like this. But it has to go through the point 0, 0, 0, so just make it go through that point. Yeah, we don't know, for example, if it's going to cross 0 or not. Maybe, yeah. If I draw it like that, 0 will have to be a critical point. I mean, we know 0 is a critical point because f prime is equal to 0 there. It's probably also a good idea for you to verify. Now, in terms of critical points, inflection points, all of that, we have two critical points, which are -5 and 0, the locations where the derivative is 0. So at those locations, we're going to need to draw the graph of our function in such a way that the horizontal line is tangent. And you can see that happening here above 5. The graph is going to look like that, as well as above 0, like this. Now, inflection point is the number -2. It's where f double prime changes sign. Before -2, the graph is a frown. After that, it's a smile. So just do your best here now to draw this graph in the best way you can. Smile up to -2 and then becomes frown. Horizontal tangent line above 5, and that's it. This is f. So you see that I tried my best to make the inflection right here, right above the point -2. Okay, wait, this is what we have to do. I just have one more like this. So now we have a function that's only defined for positive numbers after 0. And I didn't write the f prime here. F prime is the blue graph. F double prime is the red graph. You see that f double prime is a constant function, but with two separate pieces. And that makes f prime linear function with two separate pieces. Okay, what do we do here? Once again, just identify the locations where some sort of behavior change happens. And this time it's only the number 4. Between 0 and 4, the function is increasing because f prime is positive, but f double prime is negative, so it's a frown. Increasing frown like this. Now, something happens at the number 4 that the derivatives are actually not defined there. The function must have maybe a cusp or discontinuity, but the problem asks you for a continuous graph. So we're going to draw a cusp there, a sharp corner, in order for this to be undefined. Notice that the derivative is approaching 0. As you go towards 4 from the left, f prime, it tries to become 0, so the graph really is going to try to become more and more horizontal at the number 4. But then suddenly, the derivative becomes some positive number here, whatever this number is, like 4, for example. So suddenly, the slope of the graph is more like a line of slope 4. And then I know it's increasing because f prime is positive again, but this time now f double prime is also positive. So it has to be an increasing smile, shape more or less like this. So not only it has a positive slope now, and that slope is also increasing because f double prime is positive. This is what the graph must look like. I just need to do this starting at 0, 0. So something like this. This has all the necessary features, including this cusp. All right. Usually you're going to see examples like this in the book or exams in such a way that you don't actually have to draw the graphs, but rather you have to select them from a list of possibilities. So that's easier if you don't realize how much detail you have to put into this. But yeah, so I just wanted to do these ones step by step. Now a very similar problem to those. This time it's the contrary. Here's f, find f prime and f double prime. Okay, so now the one that I'm giving you is f. Sketch the graphs of f prime and f double prime. So try to look at this graph here and understand intervals where it is increasing, decreasing, concave up, concave down, as well as critical points, inflection points. So for example, in terms of increasing, what are the intervals of increase here? That would be when the graph is going up. It's between 2 and 4, this part. You can include them as closed brackets or not, doesn't matter. And then also it increases after 5. This is where it's increasing, so f prime will be positive in these locations. Decreasing would be everything else between 0 and 2. And so this first part, and also this part between 4 and 5. This is where f prime has to be negative. Critical points, locations where f prime either does not exist or is equal to 0. The points 2 and 4 have a horizontal tangent line. So f prime of 2 and 4 are both 0. But the point 5 has a cusp. F prime of 5 does not exist. With this, you have enough to draw the graph of f prime. You just need to make a function that is decreasing up until 2, then increases to 4, decreases to 5, and increases, oh sorry, not increase, decrease, but positive and negative. That's what I should be saying. Yeah, so positive between 2 and, sorry, between negative between 0 and 2. Then it's going to become 0 at 2. So something like this. We don't know if it's actually going to be a straight line or not. That really doesn't matter because we're just sketching the graph. It is 0 at 2, becomes positive between 2 and 4. But then it's going to become 0 at 4 again. So something that is positive between 2 and 4, but then 0 at 4. Now between 4 and 5, it's negative, and then it's not going to exist at the number 5. So now finally the function has to be positive after 5. We know this, but we actually know a little bit more about it because look at the original function. It looks like a straight line after 5, which means constant derivative. Whatever the slope of this line is, that is the derivative, always equal to that. So the derivative has to be a constant value after 5 and positive, whatever that value is. So this is what f prime should look like. Now let's go back to the original function to find f double prime. We're going to need to understand concavity now. Concave up. It's kind of hard to tell exactly where the concavity changes. I'm going to say it is right at the number 3 here. That looks like a reasonable candidate where it stops being a smile and starts being a frown. So I'm going to say this is concave up between 0 and 3. Then concave down between 3 and 5. And what's going to happen after 5, because the function is a constant line, constant slope, if you take two derivatives of that, you're going to get a 0. So f double prime of x is 0 for x larger than 5. Just think about it, that one derivative would give you a constant function. Like, let's say the slope is 3, one derivative would give you 3. And then two derivatives, derivative of 3 is 0. And also f double prime does not exist at the number 5 because, well, f prime does not exist at 5. Okay, so with this, you know what you have to do. Your f double prime has to be positive until the number 3, then negative between 3 and 5, does not exist in 5, and then 0 after that. So positive, negative, D and E, and 0. Some positive function here, whatever it does, then some negative function. We don't know if it goes up to 0 again or not. Doesn't matter. D and E at 5 and then equal to 0. This is a possibility for f double prime. So once again, this type of problem would actually present you a few possibilities instead of asking you to draw one. Exactly because of situations like this. Like, we don't know where we're going to start with this graph up here. We don't know if where it actually stops at the number 5. How did I know it stops exactly at 0? I didn't. So there are details that you simply don't know, but general shape should be like this. Moving on. Here's another function with a domain of everything, even though we have ln. The thing inside of this ln is always positive because of the square. So this has a domain of everything. The question is determine the intervals of up-down concavity and inflection points. So this is a question about the second derivative, concavity and inflection. We're going to need to take derivatives of this function. Okay, here are the derivatives. I needed a chain rule for the first and a quotient rule for the second. But hopefully I got them right. Now, what is the question asking again? Up-down concavity and inflection points. So up-down concavity can be done by looking at the signs of f double prime. We are going to need to understand where that function changes sign. So find, first of all, the locations where f double prime is equal to 0, because where is it going to change sign? In between those points. Okay, so what happens when you set this equal to 0? Only the numerator has to be 0. And that gives you what? X is equal to 6 over 18 is 1 over 3. When you take a square root, it can be either plus or minus root of 1 over 3, which you can rationalize as root 3 over 3. Now, for studying the sign of f double prime, you do this. Consider the 3 intervals in which those 2 points divide the real line. In each one of those intervals, the function is going to have a definite sign. F double prime is going to have a definite sign. Many ways to analyze what's happening here. Instead of plugging in points now, I'm just going to think about that. Look at the f double prime function. The denominator is always positive, so that's not going to affect your sign. You just have to look at the numerator. And the numerator is a parabola that points down because it's minus in the x squared term. So the graph of this f double prime function, or at least of the numerator of that, is a parabola pointing down. From this, you immediately know the signs should be minus, plus, minus. There's no need to actually plug in points to see, but you could do that too. Okay, but okay, what does this mean? And why did we do that? Remember, this is not f prime. I'm not gonna do the thing like this that I usually do because I'm not studying f prime. These are and critical points. These are not critical points. This the root 3 over 3 points. They were locations where f prime is equal to 0. We did this because we wanted the intervals of concavity. The answer is right here. Concave up in the interval in the middle, concave down in the others. This union with this. And finally, inflection points. Those are the points where concavity changes. So in this case, it was the 2 points that we found. By coincidence, it was actually all the points where f double prime is equal to 0. But I told you that's not always the case. Sometimes you're going to end up with a situation where maybe it's like minus, 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 never changes. So no inflection points in that case. But this finishes the problem. Moving on. Last one that I have here. Another graphical problem. Given the graph of f prime, be careful, this is f prime. Answer these questions. What are the intervals of increase, decrease of f, critical points, intervals of concavity, and inflection points? Yeah, so let's do all of that looking at the graph. Item A, intervals where f is increasing or decreasing. It's talking about f, and this is f prime. So what do we do? Look at where f prime is positive. That's going to be an interval of increase. So in this case, f prime is positive everywhere until the number minus 2. It becomes 0 there, but then it remains positive after that. So the function is still going to be increasing around that point. F prime is positive. Then there is a break in f prime. We don't know what's going to happen to f. Maybe it also breaks. So we don't know. We better stop at that point. So intervals of increase of f. You can go all the way up to the number 1. You also have to include the piece between 1 and 3. F prime is still positive in between then. I'm just not including the whole interval, like between minus infinity and 3, because I don't know if f prime, I don't know if f is also going to have a break there. Maybe the function was increasing, but then it breaks, goes down, and keeps increasing. So we have to do it like this, and decrease, intervals of decrease after the number 3 is where f prime is negative. That's item A. B is asking what are the critical points and classify them. Critical points. I've been abbreviating this word every time. Let me actually write it this time. Critical points of the function. Critical points are where the derivative is 0 or does not exist. In this case, minus 2 and 3 for values where it is 0, 1 for where it does not exist. Those are the critical points. And now we want to classify them as, what does that mean? It means local minimum, local maximum, or neither. How do we do that? By looking at f prime. Remember, if f prime, look for example at the number 3. If f prime was positive before and negative after, that means the function is doing something like this. That means local maximum. So the function goes from plus to minus, the f prime function. That means the original function has a local max there. But the other points, they are not going to be anything. For example, for the number 1, f prime goes from plus to plus again. We don't know what that's going to mean for the number 1. I mean, we don't even know if the function is defined for the number 1. So we cannot say anything there. And for the number 2, or minus 2, f prime goes from plus to plus. This time we know the function f has a value at the number -2. However, the function is increasing before it and also after it. It's like the x cubed function. This is neither. So -2 is not a local extremum. We don't know if 1 is in the domain of the function. Technically, this is what you have to write here. Don't even know if f has a value there, so we cannot say if it's local whatever or not. But then the number 3 is local maximal point. Based on what we have just discussed. All right. C. Intervals of concavity. Where is concavity, up or down? We don't have to go to f double prime to answer that. Remember that concavity can be answered by looking at where f prime is increasing or decreasing. So now we're not looking at the sign of f prime, we're looking at whether it increases or not, or decreases. Namely, f prime is increasing before -3, decreasing between -3 and -2, increasing again between -2 and -1. Then it becomes decreasing between -1 and 1, and also 1 and 3, and also 3 onwards. We don't know what's going to happen around the number 1. We should include this one as a breakpoint, because that is what it is. It's a breakpoint in whatever domain of whatever function we're talking about. A location where the functions might not be defined. So we have to go, I guess I can answer C up here so we can see this graph. Concave up is going to be between -infinity and -3, where f prime increases, also increases between -2, -1, and that's it. Concave down, where f prime is decreasing, -3 to -2, -1 to 1, 1 onwards. And that's it. Yeah, so be very careful. Once again, I'm talking about f here. When I say f is concave down, for example, in the interval -3 to -2, f prime is obviously concave up here. But the concavity of f prime doesn't have much meaning. We're looking at the fact that it decreases. You have to be careful about that. Last question, I guess it fits here. Inflection points. Where does f change concavity? So basically, when did it become from up to down or vice versa? Right here, where f prime changed from increasing to decreasing. Also changed here at the number -2. Changed again at the number -1. And that was it. We don't know about the number 1. There's not enough information here to tell. So these would be your inflection points. Okay, enough of this for today.